Okay, good afternoon or good evening. This is the last afternoon we spent together, and before to introduce the first speaker, we have 3 speakers this afternoon. Before to introduce the first speaker, I'd like to thank, on behalf of the organizer, the Fields Institute, and in particular Zara, Dudu, and Miles for the excellent support we receive in this in the process of finalizing this very interesting, stimulating conference. I think the success of this event is in large part due to the support we receive from the Fields Institute. So please join me to thank the Fields Institute for the hospitality and their professionalism. Okay, so then move to the first speaker, Sheagan John from Texas A&M University. Sheagan will talk about polynomially bounded cohomology and virtually nilpotent groups. Thank you, Sheagan.
Okay, good afternoon. And again, thank you very much to the organizers for inviting me to speak and to the Fields Institute for hosting. So today I want to speak about a subject which is maybe not the absolute main focus of one of my recent works, but ties into a lot of what has been said over the last few days. So I will start with this definition. I think Pushnig in his talk spoke about how he was able to prove certain good results where there was no bound restriction on the cyclic cohomology. But we're going to go in the other direction and speak about the importance of this polynomial cohomology bound. I want to start with the definition of polynomial cohomology as is given in Kohn and Moscovici's 90 paper on the Novikov conjecture. And here, if we say that gamma, some group, is a polynomial cohomology, if for every cocycle class in the group cohomology, there exists some generally assumed to be skew cocycle such that phi is of polynomial growth. And what it means for phi to be of polynomial growth is precisely this. That is, when we evaluate phi on any basis elements, then its absolute value is going to be bounded by a polynomial in terms of the word length on the group. So this is the precise notion. Of course, K and an R can be taken larger than necessary, but as long as we have such a polynomial bound, then we say that gamma is a polynomial cohomology. And since we're going to be speaking about cyclic cohomology, before I give the definition then of extending this polynomial cohomology to what's called polynomially bounded cyclic cohomology, I just want to review that in this particular case, and what I will be speaking about, we will use a very particular, let us say, construction for cyclic cohomology groups. That is, if we have some linear functional on the n+1 tensor product of our group algebra, and this we have a boundary map, our cyclic operator, then this forms a complex. And when we take the cohomology of it, we get our cyclic cohomology groups. And in particular, we'll be looking at delocalized cyclic cohomology groups. That is, fix some element of our group. We will generally take this to not be the identity. And we look at the subcomplex of our original complex spanned by all those group elements such that their product belongs to the conjugacy class of gamma. So this is going to be the conjugacy class of gamma. And we're going to call these our delocalized cyclic cohomology groups. So we'll keep that in mind going forward. Okay, good. So why then, what sort of relationship would we have between polynomial cohomology and these delocalized cyclic cohomology groups? Well, one of the first hints comes from the theorems of Bergilia and Nistor. And Bergilia proved this using topological methods in 85, Nistor algebraic methods in 1990. And not only do they show that there is a decomposition from the cyclic cohomology to the delocalized cyclic cohomology, where the product runs over all conjugacy classes, but importantly, they show that there exist isomorphisms with the group cohomology. So that is, we have abstract isomorphisms to, let me describe what these are. So if we have gamma in our group gamma, then Z gamma is the centralizer. We're going to call, it's going to be the centralizer of gamma. And then N gamma is the quotient of Z gamma by the cyclic subgroup generated by gamma. So that's going to be our notation here. And we have, usually you'll find in the literature that these of infinite order are called elliptic elements or elliptic conjugacy classes. We speak about the conjugacy class, and these are often called non-elliptic conjugacy classes. I'm going to just be saying infinite order and torsion. But this allows us then to say the following, that the delocalized cyclic cohomology class is polynomially bounded if every delocalized cyclic cocycle class has a representative of polynomial growth. So, and by polynomial growth, again, we are speaking about the same bound that we have for, in the case of the group cohomology. Okay, now why do these end up being so important? Well, often we want to extend the pairing. We wanted to pair cyclic cohomology with elements in C-star algebras, whether that allows us to compute certain invariants of spaces, allows us to look at things such as idempotence in the group C-star algebra. Almost, well, very often we end up needing to have some sort of pairing. And then this pairing can become quite subtle because by definition, the cyclic cocycle classes are defined on the group algebra. But we want to extend them then generally to some projective tensor norm. And as if we look away from just traces, but higher degree cyclic cocycles, then the convergence properties, how we extend, can become quite subtle. So these extensions often depend crucially on the growth properties of the cocycles. And that's where our polynomial cohomology really comes into play. So I will go through some motivational examples, and these are not at all an exhaustive list, so I apologize if I've left out anything. But one of the early results is that of Cong and Moscovici, 1990, where they proved the Novikov conjecture for word hyperbolic groups. And in fact, there they use both that these word hyperbolic groups are rapid decay and that they are polynomial growth. The idempotent conjecture, so showing that classically the group algebra has no non-trivial idempotence, and then you have the generalized idempotent conjecture for the reduced group C star algebra. G proved in 92 for torsion-free virtually nilpotent groups, and in 95 for torsion-free word hyperbolic groups, that the idempotent conjecture is satisfied. And again, this depended quite crucially on the fact that virtually nilpotent groups and word hyperbolic groups satisfy this polynomial growth condition. That way, he was able to extend certain pairings of conjoint character to Schwartz, to elements in certain Schwartz algebras. Later on, we have G. Ogle and Ramsey, who proved the Schronger-Bass conjecture for any gamma group which satisfied some nilpotent condition for Kohn periodicity operator. So I wouldn't give the definition here, but Kohn's periodicity operator which moves classes from cyclic cohomology in degree n to that in degree n plus 2. But you can show that if this takes non-zero classes to 0 uniformly for large enough n, when gamma is infinite order, then this is sufficient to say that gamma satisfies the Schronger-Bass conjecture. And just to remind that to be this normal Bass conjecture simply says that if we have a projective module over the group ring, then the rank of that over that projective module of any non-identity element must be 0. So again, a very, very strong result using a fair amount of bonological techniques actually, in addition to this. But in all three, the polynomial growth condition was an essential part. So I'm going to spend a little bit of time setting up a framework for what was, in my case, an index theoretic result, which also crucially depended on this growth condition. So I will not belabor all the details, but in the context of manifold theory, suppose that we have a spin manifold dimension n, and we equip it with a positive scalar metric g. D is our Dirac operator. We can always lift it to the universal cover of our manifold. And that allows us to speak of the group action, in particular, the fundamental group action on the universal cover, and therefore the existence of the equivariant row algebra, which is just the completion of this algebra right here. That is the Pi1m invariant locally compact operators with finite propagation. And the benefit of this is that you introduce a localization algebra, which is this C-star algebra here. So now we look at all bounded and uniformly non-continuous functions from the half interval to the row algebra. And that allows us to fit the row algebra and the localization algebra into this short exact sequence. And the benefit of that is that use localization algebra is quite a bit more amenable to computation, the KK theoretic computation, than the row algebra is directly. And so I
have a question.
Yes, indeed.
So So you said that this algebra is generated by such functions. Is it
Yes.
already sister algebra? You really have to generate by this kind of function, or is this
Sorry?
condition like being this condition look like being closed? So I'm a little bit confused. So in other words, this expression, does it yield already a sister algebra, or you really need to generate the sister algebra by this one?
Are you speaking of the localization algebra or the row algebra?
Yes.
For the row algebra, we do need to take the closure, its completion with regards to a certain norm.
Yes, but my question is about this localization algebra. So, so the collection of all possible functions from an interval to this already something which is a sister algebra with the condition that the limit of propagation tends the propagation tends to 0. Is it already a sister algebra, or you really need to generate a sister algebra using this kind of function? This is my question. I'm a little bit confused.
I think no, it is, to the best of my knowledge, generated from these F.
Excuse me?
Yeah. Let me make a quick comment. No, you have to, because of the definition, you have to take a completion.
Yes.
Because you're assuming the propagation of each element in this is finite. You see, in general, these propagations will be infinite, you know.
I see.
Yeah, you have to take a completion, yes.
For each particular T, in fact, you can have a problem. Yes. Mm-hmm. Thank you.
Mm-hmm.
Okay, so we have a construction by Hickson and Rowe, but they introduced a higher row, so a secondary, and a higher row invariant, which belongs to some K theoretic class of this, the kernel here of this localization algebra with respect to the evaluation map. And what this, so this higher row invariant captures an enormous amount of information about our manifold, about our actions on this manifold. And so very often we want to be able to determine at least whether or not it's at the very least 0. Now, to backtrack for a little bit and to get some of the notation out of the way. In the 90s, we had these wonderful results of John Lott, that under the assumption that we have a fundamental group which is word hyperbolic, or that the conjugacy class of gamma is of polynomial growth, Lott showed that this particular integral converges, and this is called the delocalized eta invariant, where this trace is given by this sum where G runs over all elements belonging to the conjugacy class, and F is a chosen fundamental domain. Now, I highlight this because, again, we see why the conjugacy class has to be of polynomial growth. For this trace to make sense, for this integral to converge, again, we needed certain growth conditions initially to ensure convergence. But we can define a higher analog of this delocalized eta invariant, and we can show that there's a relationship between cyclic cohomology pairings with this higher row invariant and this a higher analog of this delocalized eta invariant. So as defined here, we are looking only at zero-dimensional cocycles. That is, we're looking only at traces. If we want to do this for higher dimensional cyclic cocycles, then the definition needs to be, again, changed somewhat. So I will, I won't go into what precisely these two look like, but the higher analog of this eta invariant is itself, again, going to be some integral. And we get the following result. That is, we have a closed odd-dimensional spin manifold, so much the same as the for positive scalar curvature metric. And we assume that our fundamental group is virtually nilpotent. Then for cyclic cocycles for delocalized cyclic cocycles, our higher analog of Lot's delocalized eta invariant is well defined, converges absolutely. And moreover, following construction of Delahaye, Skandalis, and Keswani, there is a determinant map, a very explicit and constructive map from the K-theory or the kernel of the localization algebra to the complex numbers. This too is given by some integral which converges absolutely. And the convergence and the well-definedness of both of these integrals depends crucially on this virtual nilpotent condition, which allows us to say that our cyclic cocycles are polynomially bounded. And in fact, we can show that there is, in the special case that the K-theory element we choose here is the higher row invariant of Hickson and row, then we have this equality. I should mention that this was actually earlier proved for pi1m being word hyperbolic, and that was proved by Shen, Wang, Shi, and Yu. So a lot of the techniques that I use here carry over from the word hyperbolic case, but many of them do not. Okay, so what I want to speak about is the polynomial bounded condition itself, that is proving it for pi1m being virtually nilpotent, or for just general gamma group, proving this polynomially bounded condition which so much of this result depended upon. So here is the theorem that I'm going to be sort of giving an outline sketch proof of, and that is, if we have some discrete finitely generated virtually nilpotent group, then we can show that every delocalized cyclic cocycle class has a representative of polynomial growth. So that is, the delocalized cyclic cohomology class is polynomially bounded, and this should be an HC star, little typo. So this goes to several steps, and I must give full credit to where most of these steps come from. So we recall, maybe I'll write it here. So we recalled that there was an isomorphism in terms of the group cohomology on N gamma And this is when the order here is infinite, and this is when the order is finite. Now in 95, G was able to show the following. He showed, using, again, the fact that the nilpotent, the con periodicity operator is nilpotent for groups which are virtually nilpotent. He shows that this vanishes for all n greater than or equal to 1, given that gamma is of infinite order. So in a sense, we don't have to worry about the contribution of this term to our cyclic, our delocalized cyclic cohomology. And this is quite a technical result here. Moreover, we have, I suppose I don't have it mentioned here, but we also have G92, where he proves the following. He proves that gamma is of polynomial cohomology. If it is virtually nilpotent. And this is, he actually uses this to prove the idempotent conjecture for the reduced group C star algebra when gamma is virtually nilpotent. So the fact that gamma was a polynomial cohomology was an essential part in that proof. So we have that gamma is a polynomial cohomology, and therefore it's not too hard to show that Hn of n gamma is also of polynomial cohomology. And this gives us an idea of how we might turn this abstract isomorphism into one which allows us to preserve the polynomial growth conditions between H star and gamma, that is the group cohomology on this side, and the delocalized cyclic cohomology on this side. So one of the first steps to doing so is Lot in 92. I think, but I may be wrong, that this is one of the earliest, if not the earliest papers in which such an explicit representation was given, but he constructs an explicit representation of every element of the delocalized cyclic cohomology classes in terms of one belonging to a particular cohomology group. And I don't want to get too bogged down in the details regarding how this looks, but it allows for a very concrete approach to calculating then the growth conditions on the cyclic cocycle classes. So that's one ingredient in this step. The next one is to realize the following, that so we can construct yet another very related cohomology complex from this one. In fact, it's a little larger. And there is a polynomial growth preserving map between the two of them. So we don't need to know too much about them individually. But what we can say is that there's a polynomial growth preserving map. And moreover, that polynomial growth preserving map induces a rational isomorphism between these two cohomology groups. So I've provided what this map looks like concretely. That is, it's going to take elements in this cohomology group on the left, these cocycle classes, and average it somehow. And this summation is taken up to the order of gamma. Now, this is where the work of G becomes extremely important. If we had to worry about gamma of infinite order, then we would have a big problem in the well-definedness of this sum. It would probably become impossible to use this particular technique. But because we don't have to worry about it, that is, we know that for infinite order, all of this vanishes, and we can concentrate only on those gamma terms, those conjugacy classes, which have gamma of finite order. And so this sum is well defined, this map is well defined, and we can actually use it to prove our polynomial growth condition. Okay. Now, the last sort of abstract ingredient here is that it was proved by Nestor that this cohomology group is actually isomorphic to group cohomology, just basic group cohomology of Z gamma, that is the centralizer of gamma. So we have a few paths. One is we have an explicit representation in terms of H star C. We know that there's a polynomial growth preserving map between H star D and H star C. We know that H star D is isomorphic to this group cohomology, though this isomorphism for right now is merely an abstract isomorphism. We know that this is a polynomial cohomology because of G's result that gamma is a polynomial cohomology. And again, it's rather simple to prove that the centralizer of any element there is going to be a polynomial cohomology. And so we have, this is of polynomial cohomology. This is isomorphic. There's a polynomial growth preserving map between the two of them, and it's an irrational isomorphism, so we can move in the other direction. And then finally, we have that this group, cohomology group here, carries in it an explicit representation of every delocalized cyclic cocycle class. And so putting it all together, we should be able to get a chain of isomorphisms which are polynomially growth preserving. So the big step really is showing that this isomorphism can be represented in a way which preserves the polynomial growth condition. And to do that, and this is not, this is an idea that we see both in the paper by Shen, Wang, Xue, and Yu, but also in the work of G. Crichton and Ogle. G. Ogle and Ramsey, that we can use principal bundles to help us with this. So let me sort of outline what I mean. We have a canonical identification between the group cohomology and the singular cohomology on the principal bundle or the universal classifying space of that group. And again, this is a discrete group, so everything works out quite nicely. Life would be much more hazardous if we had like locally compact. This is a discrete group. And then we can write this again just by pure definition, the universal classifying space here. If we write it in terms of that of a principal bundle, that is, we know that there is always going to be that this is a principal bundle map. Then we can write this singular cohomology group in terms of this singular cohomology group, where this is just a fibered product or just a balanced product. So we have this explicit representation for the group cohomology of Z gamma, which we know is a polynomial group. And that is, it's very, just by definition, that follows through all the way to what we have on the left by very nerve construction. So we know that this group is going to be of polynomial cohomology. On the other hand, we can express this cohomology group in terms of a Z gamma action on the principle, on the universal classifying space with some quotient action. Again, the simpler way to think about it is in terms of these balanced products. And so we end up wanting to do the following. We end up wanting to find some polynomial growth preserving map, let's call it phi, some polynomial growth preserving isomorphism between, or at least rational isomorphism, between these two singular cohomology groups. So that is the aim. Now, to go about this, we have to be very careful with what we mean by polynomial growth actually with respect to this classifying space. We no longer have an obvious notion, but in fact, it can be stated simply as every simplex element here can be, you can take its complex coefficients. We know that we can order the points of our simplex. We can take their complex coefficients and then simply take the sum, the absolute value of the sum of these. And that actually does give you what the value, your evaluation, your absolute value of your cocycle is. And that then can be bounded polynomially. So that's the notion that we have in moving from the group cohomology into the singular cohomology. And this comes down to one main notion, and that is find a map such that if we have elements in here, so if we have elements, let's say phi 1 and phi 2, again, cocycle classes to be precise, in this left-hand side, which I will abbreviate by this. If we have these, and these are certain distance away from one another, then phi of phi 1 and phi of phi 2 are changed in distance from one another, changed in distance, no more than some polynomial bound or some polynomial growth on the distance that our original cocycles were. So that's one way that we can make rather rigorous what we mean by polynomial growth preserving in this case. So that's what we want to do. And the proof itself goes through quite a bit of somewhat tedious, simplex arguments, constructing a map from EZ on these balanced products. So I'll say phi is induced. So phi is induced by a map F, which takes EZ gamma. So it takes this balanced product to this one. And you can find such a map if one is careful. You have to do a bit of group theoretic wrangling, but one can find such a map. And we use virtual nilpotents actually quite heavily in this. But the map lifts from essentially a group theoretic argument on the simplexes themselves. Now, what this allows us to do is to say the following. Well, now that we have phi, as I said, rational isomorphisms exist between this fellow and this fellow, so we end up tensoring with Q. But we then have a map between the polynomial cohomology between the group cohomology of Z gamma, because after all, it was identical to this singular cohomology of this balanced product. And so we have a chain of rational isomorphisms which are polynomial growth preserving. Phi was defined to be polynomial growth preserving. R, again, is polynomially growth preserving. A pretty short proof can show us of that. And so we have in totality a polynomial growth preserving isomorphism from this, which is a polynomial cohomology. So we know that Z gamma is of polynomial cohomology. And therefore, this is also polynomially bounded. So and thus our delocalized cyclic cocycle classes are polynomially bounded. So that's the case of the virtually nilpotent groups, making strong use of the fact that, again, a deep result of Gromov, that every virtually nilpotent group is of polynomial growth. And that allows us to weave through all of these arguments in a coherent way.
No, you mean the result of Gromov is the converse of what you stated.
Oh, sorry, yes. Yes. So I wanted to just briefly speak about a small extension of this to direct products of groups. In particular, suppose we have a virtually nilpotent group and a word hyperbolic group. Everything here is going to be finitely generated. We can similarly show that every delocalized cyclic cocycle class has a representative of polynomial growth. And so the delocalized, again, another typo, so the delocalized cyclic cohomology is polynomially bounded. And this is going to use just, again, a few things. One being that every word hyperbolic group, where are we? So up here, G showed in 95 that every word hyperbolic, every virtually nilpotent group satisfies this vanishing condition if gamma is of infinite order. This is also true for word hyperbolic groups, again, a result of Gromov, and that's because n gamma is finite, a very deep result. And we also get this vanishing, which is going to be important. So let me go through this somewhat quickly. Okay. The centralizer of our large group gamma can be thought of as the direct product, since we are looking at a pure internal direct product, of the centralizer of gamma with respect to the virtually nilpotent subgroup and the centralizer of gamma with respect to the hyperbolic, word hyperbolic subgroup. We have this wonderful result of G, that since we are taking an extension of a hyperbolic group by virtually nilpotent group, that gamma is still a polynomial cohomology. Hence, Z gamma and N gamma themselves are polynomial cohomology. Moreover, this obvious fact allows us to use a Kunai theorem decomposition. The isomorphisms of Begilia and Nistor then take this form. The delocalized cyclic cohomology is going to be Hn of n gamma, but Hn of n gamma splits by the Kunai theorem into these direct sums. Here again, we have gamma of infinite order and gamma of finite order. And this tensor product realization allows us to do the following. We know that this does not contribute to the delocalized cyclic cohomology for gamma of infinite order on a whole. And why does it not do so on a whole? Because we know that Hn of n gamma c is equal to 0 for all n greater than or equal to 1, whether word hyperbolic or virtually nilpotent. And so when we do this over the tensor product, everything vanishes except for the n equals 0 case. And so this entire tensor product trivializes, and we are left only with the torsion part. And so the argument then can carry through in the same way that it did before. It's also pretty easy to show that if we take every cyclic co-cycle class in this, in this tensor product representation up here, is going to have some form like this. But this is a polynomial growth. That's not so hard to prove, because since both of these are polynomial growth and we are looking only at these finitely subsupported sums, then it's easy to show that this is going to be a polynomial growth. And final statements, that there exist these polynomial growth preserving isomorphisms. Again, rational isomorphisms from the group cohomology to this to Lot's cohomological construction. And in the case of the virtually nilpotent part, well, this follows from what I said above. And in the case of the word hyperbolic part, well, this follows from Chen, Wang, Xue, and Yu. And so using the Kunai theorem decomposition for the entire space, and we know that this itself is going to be, we know that this has a representation, this carries the representation for our delocalized cyclic cohomology classes. Then we have polynomial boundedness follows quite automatically from this. since we already showed that any element in here, these finite sums of these tensor products, these are going to be of polynomial growth if each of these are polynomial growth. And we know that these are from this result and from the result that I stated above. And that gives us that every delocalized cyclic cocycle class has a representative of polynomial growth in the specific case that we are taking a direct product of a virtually nilpotent group and a word hyperbolic group. Well, I think I'm maybe a minute over time, so I will stop here. Thank you.
Thank you, Sheagan.